So probabilities really are easiest by just writing out the event space and writing out your sample space, writing out the ways the event can happen, writing out the ways anything can happen in the experiment. Um, but sometimes it gets a little long to write all that stuff out. So some people like to use some different rules for combining probabilities. We're going to look at two different rules with ands and ors. So first we're going to talk about the fact that to do some of these and ors, it helps us talk about a concept called mutually exclusive. And so two events are mutually exclusive if they cannot occur at the same time. So an example would be you cannot be awake and asleep at the same time. You cannot pass a class and not pass a class at the same time. They don't have to be complements of each other. They can just be things that can't occur at the same time. Such as I cannot pick from a deck of cards, I cannot pick a spade and a heart at the exact same time because I'm picking one card. And that one card cannot be a heart and a spade at the same time. So that's kind of what mutually exclusive means, is they can't occur at the same time. Knowing that, we can use something called the addition rules. And again, I will stress that I don't use these rules unless it really makes life a lot easier. Most of the time, I actually just write out the different ways the event can happen, the different ways the outcome, the sample space can happen, and then just count. And that makes probabilities much easier, but you can use this if you want to. So if you're looking for the probability of A or B, so this is an or statement because we can either do A or B. And that means either A happens or B happens or both happens. And so if you have any events, then the probability of A or B is the probability of A plus the probability of B minus the overlap, probability of A and B. A and B would be that overlap. So you would actually subtract off that overlap that would be happening because otherwise you counted it twice. If A and B overlap, then you counted probability of A and probability of B includes that overlap. So you subtract off that overlap. Again, I don't use these rules unless I want to. Usually I don't want to, but they're there if you want to use them. If A and B are mutually exclusive, then there is no overlap, in which case this term here is not there. So looking down here, you're going to see the probability of A or B is just the probability of A plus the probability of B because this one is gone. It's zero because there's no overlap. So this is kind of what we're looking at. Here is A, here is B, and here's that overlap. So we got to subtract off that overlap because we counted it twice. If they're mutually exclusive, here's A and here's B, and notice there's no overlap. So let's do some examples. Suppose you roll a single fair die. What is the probability of getting a 4 or a 5? And so if I'm rolling one die, they're definitely mutually exclusive because I can't roll a die one time and get a 4 and a 5 at the exact same time. So they are in fact mutually exclusive. So the probability of A or B is the probability of A plus the probability of B. The probability of a 4 or 5 is the probability of getting a 4 plus the probability of getting a 5. And the probability of getting a 4 is 1/6. Probability of getting a 5 is 1/6. They add to 2/6. Again, if you want to reduce and make it into decimals and percents, you can. I prefer the 1/6. That means the 2/6. I also prefer to just write out, if my event is getting a 4 or 5, I can write out that there's a 4 or 5. There's my event, and there's two of them, and then my sample space was all the different sizes, and there's 6 of those. So again, it's just as easy to do 2 out of 6. So let's do another example. Let's say a card is drawn from a standard deck. What is the probability of getting a king or a heart? And so so the first question is, are they mutually exclusive? And the answer would be no, because I can get a king that is also a heart at the same time. If I pull one card from the deck, that card could be a king and a heart at the same time, mainly the king of hearts. So I would have to use the other formula. So the probability of a king or heart would be the probability of getting a king plus the probability of getting a heart minus that overlap of both of them together. In a deck of cards, there are 4 kings. In a deck of cards, there are 13 hearts, which means I just counted the king of hearts twice. I counted it here and here, so that's why I subtracted the 1 out of 52 off. That gives me 16 out of 52, or again, if you want to reduce it. You can also, like I say, do this by just writing it out. There are 4 ways to get in the king. So the king of hearts, king of spades, king of diamonds, king of clubs, and then there are 13 ways of getting a heart, 2 of hearts, all the way through to jack of hearts, or actually jack of hearts, yeah, do jack of hearts, queen of hearts, and I don't want to put the king of hearts again because I already have the king of hearts. It's right there. And so then I just have the ace of hearts. So there are 2 through jack, which is 2, 3, 4, 5, 6, 7, 8, 9, 10. Jack, queen, king. I'm sorry, jack, queen, ace. So there's 12 cards here, 13, 14, 15, 16. So notice I also get the 16 out of 52. So we call that using, we're going to talk about using that, but let's talk about independent events now. So addition roll is for ors. Independent events will be dealing with ands, but it also has some other pieces to it. The outcome of one event does not affect the outcome of another event, or the probability of the other event. So we talk about the multiplication rule for independent events. If A and B are independent events, then the probability of A and B is just the probability of A times the probability of B. So again, the idea of independence is that one doesn't affect the other. Knowing you got a head when you flip a coin doesn't affect the probability of getting a head the very next time because it doesn't remember what it did. When you play craps, or not craps, but slots at the casino, your slot machine doesn't remember what it just gave you, so the probabilities don't change with each roll or each spin of the slots. Having children doesn't affect it. Knowing that you have a girl, your first child, will not affect the probability of you getting a girl, the second child. Another example of dependent events would be the probability of your electricity being out. If you know that your refrigerator is out, does that change the probability that your electricity might be out? Well, maybe, especially if your lights are out. But it gives you an idea that it could be that the electricity is out, or it could be that your refrigerator is broken. So there are 2 different things that could happen, but the probability does change. Knowing somebody has the internet in their home does change the probability that they have some kind of device that uses the internet. Because otherwise, why would you get the internet why would you pay for internet if you didn't have some device that used the internet? So those are kind of examples of places that are dependent events, and these are events that are independent. So again, if they're independent, then the probability of A and B is just the probability of A times the probability of B. I, again, don't use this rule unless I have a really big sample space I'm working with. Usually I just write them out. I can write out the probability of A and B happening quite easily, and usually I do that and don't use this formula. So let's do an example. Let's say we have 3 fair dice are rolled. What is the probability that they are all ones? So here's an example where I wouldn't want to write it out because there would have to be, I'd have to write out each way of getting 3 fair dice rolled. Well, 2 fair dice gave me 36. 3 fair dice would give me even more outcomes, actually 36 times 6. So it'd be huge, and I wouldn't want to write them all out. So this is an example where I would use this. Are they independent? Well, yes, because the dice don't remember what they rolled the time before. So the probability doesn't change just because they rolled something. So probability of getting 3 ones means that you get a probability of the 1 being on the first, a 1 on the second, and a 1 on the third. Well, each die has a 1/6 chance of getting a 1 on the first, so it's 1/6 times 1/6 times 1/6, or 1/6 cubed. You can either leave it as 1/6 cubed, or you can write it as 1 out of 216. Again, you can write them in decimals if you want. What's the probability of rolling 10 sixes? Well, the same kind of rule. You had 3 sixes was 1/6 times 1/6 times 1/6, or 1/6 cubed. So 10 sixes would be 1/6 to the 10th. Again, you can write this, leave it as 1/6 to the 10th. You can write what 6 to the 10 is, or you can write it in scientific notation. It's up to you on which one you want to do. I prefer to just leave it with the 1/6 to the 10th. So I would leave my answer just like that. So now let's say a card is drawn, replaced, and another card is drawn from a standard deck. What is the probability that they are both aces? So that means you're looking at the probability of an ace on the first card and an ace on the second card. Are these independent? Well, yes, because you put the card back. Since you put the card back, you haven't changed the probability of getting an ace on the second card, knowing what you got on the first card. So all you have to do is multiply the probability of an ace on the first times the probability of an ace on the second. There are 4 aces in a deck, so it's 4 out of 52 times 4 out of 52. Again, you can leave the answer in any one of these methods. And this is where I use this probability, this formula, is in situations like this. All right, so if they're dependent, by the way, then things do change. So I do want to point out, if I didn't put the card back, if that card didn't go back, then let's look at that probability. So what's the probability of 2 aces without putting the card back? Well, it's still the probability of an ace in the first. Times the probability of an ace in the second, but because we now removed that card, that does change that probability. So the second one is going to be affected by what the first one was. So these are not independent events because I didn't put that card back. So the probability of an ace on the first is 4 out of 52. But the second card being an ace, assuming the first card was an ace, does change. So we actually can say this given ace on the first. And since there were 4 aces, but now we're assuming the first card was an ace, there's now only 3 aces in the deck. And instead of being 52 cards, there's now only 51 cards. So that probability would be 3 out of 51. And then you still multiply them together. So you're still using that rule. It's just you can't use the rule of this being just independent events. You have to think about what is happening. Okay? The last thing I want to look at is the probability of the at least once rule. If an experiment is repeated for let's say n different trials, and the probability of an event A is probability of A for one trial, then the probability of A occurring at least once is 1 minus the probability of the complement to the nth power. So as an example, let's say we have an example where the probability that a son forgets his homework is 20% of the time. So the son forgets his homework 20% of the time. And we'd like to know, therefore, the probability of A, where A is the son forgot his homework, is 0.2. The probability of him not forgetting his homework is 1 minus 0.2, or 0.8. What is the probability he will forget his homework at least once in the next 10 school days? So it's not just 0.2 a bunch of times, because he may not forget it each time. So it actually is using this rule, the probability of at least once, so at least one time he will forget his homework, is 1 minus the probability of a complement, not forgetting his homework, to the 10th time, because we want to do it for 10 school days. So it's 1 minus 0.8 to the 10th, or 89.3% of the time. So it's 89.3% of the time that your child will forget his homework at least once in the next 10 days.